London dispersion forces. Also, you may hear that it's called dispersion forces, London forces, instantaneous dipole-induced dipole forces, or sometimes very vaguely called van der Waals forces, which most exam boards still accept an answer, but I would call them London forces just to be specific. Anyway, these are a type of intermolecular attraction, right? So they're an intermolecular force, so between the molecules. So let's remind ourselves of the basic structure of an atom. In the center, we have a nucleus surrounded by this cloud of electrons, right? This is another picture. So in the center, we have the nucleus surrounded by this cloud of electrons. And as you can see, these electrons are not still, right? They're not static. They're constantly moving. And at some point, this causes an asymmetrical distribution of the electrons around the nucleus. Does that make sense? So they're not just evenly spread out. They'll be constantly moving at some point. They'll be pushed to one side just for a split second. And what this does is it means the side where the electrons are more dense, it gives us a slight negative charge. And the side where the electrons are not present as much, it gives it a slight positive charge, right? So that's the asymmetrical distribution. And this is what's known as a temporary dipole. So when a second atom / molecule comes close to this temporary dipole, so this is our temporary dipole here with the electrons distributed on one side and the partially negative charge. When a second atom comes near, what happens is these electrons get pushed away by electrostatic repulsion, right? So it's like charge, both negative charge. These electrons on this new atom get pushed away. And what this does is it induces a negative charge on this side, a slight negative charge, and a slight positive charge on the side without the electrons, right? And this is known as an induced dipole, right? So this is our temporary dipole on the right and the induced dipole on the left. So now, because there's a slight difference in charge, it allows this electrostatic attraction to occur between the two atoms. And that's what is known as our London force. And I should have mentioned that London forces are present in all molecules, all right? All molecules, polar or non-polar, they're present in all molecules. So there are two factors that determine the strength of these London forces, all right? The first one is size. So larger molecules, right? We're using two atoms here. The larger one tend to have stronger London forces. Why is that? And this is due to what we call an increased polarizability, which basically just means it has an easier tendency to form a dipole. And this is because in the larger molecules, the electrons on the outside, they're further away from the nucleus. So they're held less tightly, if you will. And that means they can move more freely and therefore more likely to form dipoles, right? And the second factor is molecular shape. So to illustrate this, we have two structures. So we have neopentane, which is this spherical structure, and we have N-pentane, which is this broad cylindrical structure. Well, they both have 5 carbon atoms and 12 hydrogen atoms, right? So they have the same molecular size. But as you can see, the boiling point for N-pentane is higher than neopentane. And actually, at room temperature, neopentane is a gas and N-pentane is a liquid. So why is this? Well, this is because of the cylindrical structure of N-pentane. It means it has a greater surface area for contact. Hopefully you can appreciate this compared to the spherical neopentane. When a second molecule of N-pentane comes close, it has a greater surface area to form these London forces. Yeah? Compared to this one, this is a lower surface area because of its spherical shape. It could form fewer London forces. And because N-pentane can form more London forces, it means more energy is required to overcome these bonds. And that's the reason it has a higher boiling point. Okay, so I hope that helps your understanding of London forces. If you have any questions, you can visit my website or email me, which will all be in the description below.